You know what's up. Research methods. Oh, yeah, I know. You've been waiting for this all semester, all 2 weeks of it. Here we go. Got that, and we got that. All right, so we're going to see this slide a little bit later when we talk about replicability, but I wanted to show it to you. Make it a little bigger. Bloop. And this is the hierarchy of evidence as seen by scientists, right? So you see at the very bottom, anecdotal reports or stories. And if you don't remember what anecdotes are just personal stories, right? So, oh, I know a person who fill in the blank weird psychological phenomenon. Okay, well, that's an anecdote. And I believe that you know somebody who is like that, right? Other anecdotes that start to get you in trouble is, oh, everybody I know does X, Y, or Z. Now we're getting into this false consensus folk psychology world. So how do we overcome that? Well, you do systematic observations. Okay, well, that's good too, but it's not really a way of collecting data, right? Case studies are another way that you can just observe and collect information, but it's not data quantized numbers that you could analyze. But you could do correlations, and that's kind of what falls under the uncontrolled outcome studies. If you are writing everything I'm saying down in a panic, please know that I'm about to unpack everything that I'm saying. Okay. I left off at uncontrolled outcome studies. Those are like correlations. This variable is correlated with this variable. It's called uncontrolled because the researchers aren't able to control for what are called confounding variables. You will know what that means in a few minutes. When you can control the variables, it is called a randomized controlled trial. When many randomized controlled trials have been done on the same topic, they can be put into what's called a meta-analysis. A what? Meta-analysis. So this is the hierarchy of evidence. And another way of breaking that down, or more appropriately, the way it's going to be broken down for this class, is we're going to think about research methods as falling into one of three buckets. Not that these buckets are exclusive, but for the purpose of teaching this topic, we'll pretend they are for a little bit. So we can either observe, and observe it could start with anecdotes and move on to naturalistic observations and case studies, and we can send out surveys. And then a step above just observation is the attempt to predict. These are the correlational studies. And a step above observing and predicting would be controlling. And it is through controlling your variables that you are performing an experiment. This is the gold standard of the gold standard of the gold standard. No, seriously. So it is the gold standard of the way to test a theory, which is the gold standard of science, the truly super fantastic way of testing almost anything in the natural world. So let's move on with the show. Starting with the first research method that falls under or into the bucket of observing. First, we're going to be looking at things that are qualitative instead of quantitative. You heard me say a moment ago that, there's nothing quantized. There's no numbers involved in some of this stuff. And so if you want to think of it as two sides of the same coin, all data is a coin. It has currency. Some of it is qualitative data, and some of it is quantitative. Quantitative, like I said, is numbers. Qualitative is if you're observing a child, you want to know, what things do they pick up? What do they do with those things? How frequently do they pick up those things? Do they recruit their friends to help them play with those things, right? These aren't things that you can, unless you're coding for that behavior, put into numbers. So that might be considered qualitative. So as we'll see, an experiment is a very specific thing with very stringent criteria. So let's start on the looser end of things, on the non-experimental ways of getting information. And these techniques, as I mentioned, will mostly be considered qualitative methods because researchers collect data based on the observation of everyday events, like written accounts of observed behaviors, as in naturalistic observations, or maybe a case study where you have the descriptive records of one or more individuals' experience and behaviors. In other words, it's not numerical like quantitative data. And we're going to get into quantitative methods a little bit later. It starts with correlations. Let's not get ahead of ourselves. For developmental psychologists who observe children in the playground, social interactions, gestures, and behaviors, there may not need to be a way to calculate the quantity of any event during the naturalistic observations, because it is the quality of the habits, gestures, and interactions that are of value. What snacks were eaten? Again, did they recruit the help of others? How did they do that? Etc. When your naturalistic observations revolve around a single individual, generally someone with unusual characteristics, you're engaged in a case history or a case study, which makes up most, if not all, of the work Sigmund Freud used for his psychoanalytic theories. Case histories do continue to be a valid method for unusual clinical cases, but as a starting point for broader research questions about a specific characteristic. The most famous case study in psychology is the pictures that are in the background of this slide, and that is a gentleman by the name of Phineas Gage. Phineas Gage had an iron rod pierce his head, taking with it a very specific chunk of his brain, changing Phineas Gage's personality. We're going to be talking more about Phineas Gage later in the semester, but please let it be known that because he lived through that experience, he was considered a case study to demonstrate that there are parts of the brain that have specific functions, and the deficits in Phineas Gage's behaviors could be directly related to the parts of his brain that were removed from the iron rod going through it. All right, let's quickly review 3 problems with naturalistic observation and case studies. First, statistical analyses can't be used if numerical data isn't generated. Second, if quantitative data were collected, these would be at best correlations. So inferring causality would be impossible. And lastly, these non-experimental and qualitative methods are prone to inconsistencies. Once we move to quantitative methods, we can start doing things like, well, we can send out a survey. And based on the questions that are asked and the answers that are provided, you can describe how a population feels about certain topics. So one way to avoid the problems that I just talked about with the observational methods is to collect data on an instrument that is both reliable and valid. And this brings us to this territory here with a survey. And a survey is, again, the beginning of a quantitative method that collects numerical data that's going to be used for statistical analysis. So when using an instrument to collect data, there are many factors to consider. You have relevancy, reliability, and validity. And by the way, when I say instrument, you can either think of a physical instrument like a brain scanning machine or a heart rate monitor, or you can think of something like a survey or a rating scale that gets filled out. These are all data collecting instruments. Whatever the end result of this instrument, are they predicted in a straightforward way by the hypothesis? For example, why would you collect someone's heart rate unless you expect it to change in some meaningful way, right? So that is the validity, the relevancy of what you're collecting to what you're asking. Why would you collect something like reaction time when your hypothesis is about personality? Your instrument should collect data relevant to your hypothesis. It should also be reliable and valid. Hold on one moment. Oh, stop spazzing out on me. So I just mentioned that your instrument should also be reliable and valid. Reliability refers to the consistency of a measured variable. That is, does the score remain consistent for the same person if they're retested at different days and times? This kind of reliability is called retest reliability. I can't believe I didn't make a slide for any of this information. And retest reliability, for that, you can think of your scale at home. If it read a different weight every time you stepped off and back on it, even if it was like separated by seconds, it wouldn't have very good retest reliability. You want your instrument to behave consistently each time you use it. If two different researchers are observing the same behavior and using the same instrument, the same scale, to measure that behavior, do they get the same results? That's a different kind of reliability. That's called inter-rater reliability. And of course, you want the answer to this to be yes, right? You want your instrument to behave consistently regardless of who is using it. Okay, assuming we have an instrument that is relevant to the hypothesis and produces reliable data, we need to address its validity or legitimacy. Can effects within the experiment be attributed to the variables that the researcher intentionally manipulated? Is your manipulation making a difference on the variable your instrument is measuring? Oh, my alarm clock is going off. Be open to connecting with your family on their terms. Okay, that sounds like a great idea. So we're talking about internal validity. Internal validity refers to the extent to which you can trust the conclusions that have been drawn about a relationship between independent and dependent variables. Finally, how widely can the findings be generalized? Right? So we just talked about internal validity, where like it needs to make sense what you're saying about your hypothesis and the variables that you're collecting. Once you have your results, do they make sense to the outside world? That would be external validity. External validity refers to the extent to which the results of a research design can be generalized beyond the specific way the original experiment was conducted. Don't try to write all that down. Just know internal validity. How do the variables relate to each other? External validity. How do your results relate to the outside world? There would be nothing worse than to demonstrate something awesome that only happens in your lab. Well, that's not really valid information, because how many people are hanging out in your lab? Not the whole humanity. Okay. Once we have an instrument that meets our criteria of relevancy, reliability, and validity, we can begin collecting data, and we will start with the survey. Okay. Now, let me take a sip of seltzer. Surveys. Survey can be thought of as a study of the prevalence of certain beliefs or attitudes or behaviors based on people's responses to specific questions. That is, it's a report of people's answers on a questionnaire. And it's easy to conduct, but unfortunately, it's also easy to deceive people on a survey. Survey results are affected by a few things. One of them was the sampling. Getting a random or representative sample is important with surveys, right? Because if you give a survey to a small sample of people that don't represent the population, the results can make the population look like a bunch of wackaloons. Another thing that affects survey results is the seriousness of those being interviewed, with the assumption that those who take the survey more seriously will provide more genuine and trustworthy answers. And then finally, the thing that I really want to focus on is the thing that can really affect the results of a survey are the wording of the survey questions. And this presents a problem in doing surveys called surveyor bias. This happens when the wording of the survey question encourages answers that the surveyors hope to receive, rather than being an honest reflection of the thoughts provided by the participants. If you don't know what I'm talking about, just think about how differently you react to the same question asked differently, right? Hey, did you set the table yet? Right? That could be one way of asking a question that you don't necessarily think is good, bad, or other, right? But if somebody's like, you haven't set the table yet? Well, that's also a question, but now it sounds a little accusatory. It's getting at the same answer. So that is an example of how just asking a question differently is going to evoke a different response in the participant. That can be used to manipulate. Now, before we go into, because I have that. Here we go. Before we go into the surveyor bias. So there is a book, story time. When I was taking statistics, there was a book that was provided, and it is called How to Lie with Statistics. I'm literally looking for it right now. It's somewhere in this room. Dagnabbit. Anyway, they don't really use that in statistics anymore, statistics classes. Some of the examples are super outdated or whatever, but I think it's a wonderful book. So I made some slides from that book, and I use them to supplement this material. So let's take a look at what they have to say. So again, this is a book that you don't have, called How to Lie with Statistics. So I said that sampling could be a problem for surveys. Here's an example that they give. If you have a barrel of beans with some of them red and some of them white, there's only one way to find out exactly how many of each color you have. Count them all. But you can find out an approximate amount of red versus white if you pull out a handful and just count that sample of that population, assuming the proportion will be the same. If your sample is large enough and selected properly, it will represent the whole well enough for most purposes. Now, if you're not doing a random sample, then, like I said, you don't know whose opinions are being represented by a survey result, right? Does every name or thing in the whole group have an equal chance to be chosen in the sample? If not, then you should really think about. So if a conclusion comes at you, you're reading something, 67% of Americans are against something. You should read that as, well, 67% of which Americans? Because if you just ask Americans from this part of America or the other part of America or another part of America, their opinions aren't going to be reflective of the whole country. So 67% of which American people think this thing, brother or sister or friend? All right, now we're talking about surveyor bias. Look at these questions and just think about what kind of answers they evoke. The difference between where do you like to party? Well, that assumes that you party. Don't you think a more neutral way of asking that would be, what do you like to do on weekends and evenings? Right? How happy or unhappy are you with the rate of current school board funding and the Common Core curriculum? Well, you just jammed at least two questions into one. So that answer is like, how are you going to be able to discern which half of that question is being answered. It would be better to break it up. How happy or unhappy are you with the rate of current school board funding? And next, what do you think of Common Core? Last example, do you always shower before bed? That almost sounds accusatory. Another way of asking, getting at the same answer is, how many nights a week do you shower before bed? Some people don't shower before bed. Some people shower when they wake up. Some people do both. All right. So I think that from these examples, it's pretty obvious to see how surveyor bias could change results. Well, how do you analyze data that you've collected from a survey once you've collected it? Well, you could either just do descriptive analyses, which I will talk about in a little bit, which is exactly what it sounds like. It uses statistics to describe what's happening. This percent of people said this compared to this percent of people said that. Or you could use correlational analyses. A correlational analysis tells you whether two variables are related and how strong that relation is, if it exists. To measure the strength of a correlation, researchers use something called a correlation coefficient. Again, if you're at a dinner party and you bust out correlation coefficient, everybody who's a science nerd, their ears are going to perk up. I don't know necessarily if that's something you want, but I'm just saying. So a correlation coefficient is a mathematical estimate of the relationship between two variables. A coefficient of +1 or -1 indicates a perfect relationship. That is, if you know the value of one variable, you can predict the other with perfect accuracy. In psychology, you're likely not going to come across +1 or -1 correlations. And here's some examples of scatter plots. And scatter plots are used to show correlations. And there are 3 different kinds of correlations being demonstrated here. And in case you wanted to know exactly what this is, if you look at the y-axis, the one on the far left going from 0 to 100, from bottom to top, those are the scores of a class on their final exam. And then on the x-axis, the one that goes from left to right, you will see in that far left graph the first test score. So you can see how the first test score, having a positive correlation of +0.72, it looks like, if you were to draw a line through it, it looks like the line would start at 0 and go linearly to 100. Another way to say that is, for every increase on the x-axis, there is an equal increase on the y-axis. Moving on to the next one. Now we're plotting your final exam score to the amount of absences you've had. Well, this one looks like kind of the opposite. If I were to draw a straight line through that data, it would start at 100 and go down into the right until it hit that 30. So that's a negative correlation of -0.44. And another way to say that is, as one variable decreases, the other variable increases. So as it applies to absences, the fewer absences, the higher your final exam score. The more absences, the lower your final exam score. And then finally, if we just looked at your last 3 digits of your Social Security number, or at least the last 3 digits of the Social Security numbers of the students in this class, and you graph that against the final exam score, there's no correlation at all, because why would there be? The other two make sense. Your first test score is a predictor of how well you're going to test in general. So it's positively correlated to the final exam. That makes sense. The amount of absences is going to impact how well you're going to do on an exam. So that also makes sense. More absences, lower final exam score. Hint, hint. And then the last 3 digits of your social security number, that has nothing to do with your ability to take tests or absences or anything like that. So there shouldn't be any correlation, and there's not. The R equals 0.08 on the far right scatter plot. Now, unfortunately, just because we know that two variables, A and B, are related, this does not mean that we know which variable is affecting the other. That is, we don't know the direction of causality. It could be that A causes B or that B causes A, which is something called the directionality problem. The change we're seeing could be caused by some third variable as well. And this is called the third variable problem. Now, an example of the third variable problem, think of it like this. How much sunscreen people use is positively correlated with their chance of getting skin cancer. Let me say that again. How much sunscreen people use is positively correlated with their chance of getting skin cancer. Does this mean that sunscreen causes cancer? It's more likely, think about this, that people who are at risk for skin cancer because they spend a lot of time in the sun are also ones that use more sunscreen. So it's not the application of sunscreen that's causing cancer. It's the being outside all the time that causes cancer. But you need to use a lot of sunscreen if you're going to spend a lot of time outside. So there's that. Here's another fun one. The number one predictor of motorcycle accidents is tattoos. Do we conclude that, one, tattoos cause accidents, or two, that motorcycles accidents cause tattoos? That would be weird. Maybe there's a third variable, like, come on, work with me, risk-seeking behavior. Risk-seeking behavior accounts both for the kind of personality that would get tattoos and one that would get motorcycles. And motorcycles, of course, if you own one, there's a likelihood of getting into an accident. And if people with tattoos are the ones getting the motorcycles, the ones getting in accidents also have tattoos, having nothing to do with tattoos or motorcycles, but everything to do with a third variable, risk-taking behavior. Bwam, bwam, bwam. A final problem with correlations is that you can perceive an illusory correlation. And this is the little infographic at the bottom there. This whole idea that sugar makes kids hyper is incorrect. It looks that way, right? Hey, my kid is hyper. My kid just ate cake and ice cream. Cake and ice cream have sugar. Sugar must make my kid hyper. That's almost like a logical syllogism, but it's not the case. You're observing your kid being a super freak while being overstimulated, but there is no connection between hyperactivity and sugar intake. Yet, we will hold on to that knowledge provisionally until more studies come about to falsify that theory. All right. And one thing I did want to draw your attention to, this correlation in the background. This is a very fun way of demonstrating that just because things are correlated does not mean that one thing causes the other. So this one shows that the age of Miss America, you know, the woman who wins Miss America, is correlated to the amount of murders by steam, hot vapor, and hot objects. They're correlated. Does that mean that one causes the other? Does that mean that we can reduce or increase the amount of murders by steam, hot vapors, and hot objects by selecting Miss Americas of different ages? The older they are, the more murders. The younger they are, the less. Maybe we could get rid of murders by steam, hot vapors, and hot objects if we award infants the title of Miss America. They would be 0 years old. And therefore, correlation being what it is, no, correlation does not mean causation. I hope you had fun with me on that one. It's silly. This is silly stuff. But this is what feeds into folk psychology. I got to teach it. All right. Now, moving back to the How to Lie with Statistics book, they have their own version of saying what I just said, and they call it the post hoc fallacy. To avoid falling for the post hoc fallacy and thus end believing things that are not so, you need to put any statement of relationship, right? That's a correlation. You need to put any statement of correlation through a sharp inspection. First, ask, is it due to chance? Second, does A cause B or does B cause A? Next, is there a third variable that accounts for this correlation? And then finally, the correlation could be inferred to continue beyond the data with which it has been demonstrated, right? So if variables A and B are correlated, some people might take that as evidence that variables A and C are correlated because B and C are so close to each other. That's not the case. Now, before we move on to experiments, here's another way to think about the research methods that we've gone over so far. A case study is a detailed description of a single individual. A naturalistic observation is a description of behavior under natural conditions. A survey is a study of attitudes, beliefs, and behaviors based on answers to questions on a questionnaire. And correlation studies describe the relationship between two variables. Now, one last thing I want to say about correlations, with limitations aside, correlational analyses are very useful still for populations and questions that are difficult or unethical to pursue in the laboratory, like looking at the detrimental effects of cigarette smoking or alcohol abuse during pregnancy. We do not live in a world where studies require people to smoke cigarettes or drink alcohol to the point of harm or unnecessary risk. Instead, we can use correlations to look at data of people who unfortunately already are living that lifestyle to demonstrate links from occurrences in real life. All right. Now we have made it. We have made it to the experimental research method. And I'm going to end this here because we're at 30 minutes and we're going to start fresh with a lecture about experiments. Yay! Experiments.